All right, this is part 3 in our discussion about molecular geometry. We've got this rather complicated looking molecule here, and the question says, based on the molecule above and your knowledge of the Vesper model, predict the bond angles for each of the following bonds. Now we have to look carefully here. We've got to find H sub x, which is in the lower left-hand corner, where it goes up to the carbon marked Y and then the carbon marked Z. And what angle would that be? Well, this carbon is got 4 single bonds attached to it. So we know that this means that it's a tetrahedral arrangement, and therefore the bond angle for tetrahedral is 109.5. We look at the second one. I want to go to the hydrogen marked A, which is sort of off in the lower right corner, up to carbon B, and then up to or down to carbon C. So when I look at this carbon that's in the middle has got 3 domains, and so we would expect that this would be a trigonal planar configuration, and the bond angles for trigonal planar are 120 degrees. And the last one, CP to CQ to N. CP is the carbon in the ring that's kind of on the upper right-hand side, up to the right, CQ, and then over triple bonded to the nitrogen. When I look at this arrangement, I see that there's really just 2 domains, but I've got 2 bonding and 2 non-bonding orbitals on the carbon, and this is going to give me a 180-degree angle. Even though it's not printed this way, this is an artifact of a word processing program, we would expect that that angle would be 180 degrees because this is a symmetric bond. All right, now let's take a look at the next section, molecular shape and polarity. And we've got 3 quick questions here. Part A, the carbon-oxygen bond and the hydrogen-oxygen bond are polar because the atoms in the bond have different electronegativity values. So they aren't shared equally, and therefore we get a dipole created. Polarity in a molecule is caused by this asymmetry, this difference in electronegativity. Question B says the carbon dioxide molecule is nonpolar because although it has 2 dipoles, and the dipoles themselves indicate a degree of asymmetricness when it comes to electronegativity differences, the fact is that both of these dipoles are equal in strength but opposite in direction. They cancel each other out, and the entire molecule taken as a whole is symmetric, and therefore it's linear. Part C says the water molecule is polar because although it also has 2 dipoles between oxygen and the adjacent hydrogens, they're equal in strength, but they don't point in opposite directions. And this is because of the 2 non-bonding pairs on the top of the oxygen atom. And this causes asymmetry, which causes polarity. All right, you can take a look at these little pictures here and see what we're talking about with the construction of the model of the bond between these atoms. All right, part D, kind of a long question. It says identify the shape of each molecule and classify it as polar or nonpolar. I couldn't get all of them on the same slide, so we'll do some of them on this one and some of them on the next one. We've done some of these before, so this will go relatively quickly. Carbon dioxide has got 2 bonding domains around the central carbon atom, no non-bonding domains, therefore it's linear, and because it's symmetric, it's nonpolar. I'm showing, rather than typing it out, I'm just going to write NP. All right, hydrogen cyanide, 2 bonding domains, no non-bonding domains. Again, it's linear, but because it's asymmetric, a different electronegativity difference between carbon-hydrogen and carbon-nitrogen, this becomes a polar molecule. Boron trifluoride, we've seen this before, 3 bonding domains around boron, no non-bonding, and therefore the fluorines are all separated by 120 degrees, and we have trigonal planar. And because they are all symmetric, this is a nonpolar molecule. All right, phosgene, CCl2 double bond O. I've got 3 bonding domains around the central carbon, no non-bonding, and it becomes a trigonal planar. But again, because I have dipoles that are not equal and opposite, the 2 chlorines are equal, but they don't point in opposite directions, and certainly they are not the same as the carbon-oxygen dipole. Therefore, this is a polar molecule. All right, sulfur dioxide, 2 bonding orbitals or 2 bonding domains, 1 non-bonding, and this causes it to be bent. And because it's bent, it certainly is going to be polar. All right, methane. We've been down this road a couple of times. Methane has 4 bonding domains, no non-bonding domains. Its shape is tetrahedral. And because all of the domains point in opposite directions, vectorially they add up to have no net dipole, and so this is a very nonpolar molecule. Now we look at the next one. This is chloromethane. Chloromethane just has one of the hydrogens from methane taken off and substituted with a chlorine. So we would expect that this would be very similar to methane, and it is. But the difference is that because we've got a difference in electronegativities, the carbon hydrogen to carbon chlorine, we would expect a net dipole to exist on this molecule, and it does, and that gives us a polar molecule. All right, next one is ammonia, NH3. 3 bonding domains, 1 non-bonding domain, trigonal bipyramidal in its shape, and because our trigonal pyramidal in its shape, and you would think if it's trigonal pyramidal that there would be a non-polarity about it, but it is polar because it's got the 1 pair of non-bonding electrons, and that gives it a net dipole. All right, water, we know what we're doing here. Water's got 2 bonding, 2 non-bonding. It's bent, and it is in fact quite polar because of the way that the non-bonding pairs force the bonding pairs down. This whole thing is quite non-symmetric. All right, we'll go to the next slide here, but it's a continuation of what is printed out. Here we're looking at phosphorus pentafluoride. I've got 5 bonding domains, no non-bonding domains. Trigonal bipyramidal is our shape. It's very symmetric, 1 up, 1 down that cancel each other, and 3 at 120 degrees around the equator, so a nonpolar molecule. Now, we would expect PF4Cl to probably be polar because we've substituted one of the fluorines for a chlorine, and that gives us the 5-0 configuration in terms of domains in the trigonal bipyramidal, but because it's asymmetric, it's going to be polar. All right, the next one is sulfur tetrafluoride. I've got 4 bonding domains, 1 non-bonding domain. This is going to be a seesaw configuration and it's going to be polar because it's got a non-bonding domain. Chlorine trifluoride, 3 bonding domains, 2 non-bonding domains. This gives us a T shape. It's shaped like the letter T. And because it's shaped like the letter T, and because I've got non-bonding domains it's going to be polar because it's quite asymmetric. All right, xenon difluoride. 2 bonding domains, 3 non-bonding domains, but it's linear. And it's linear because xenon is one of those exceptions. Xenon can have more valence electrons around its outside shell. Our next one is sulfur hexafluoride. We've seen this before, 6 bonding domains and no non-bonding domains. This is an octahedral shape, and because there is symmetry all the way around in both the axial and the equatorial directions, this is nonpolar. Bromine pentafluoride, I've got 5 bonding domains and 1 non-bonding. It becomes a square pyramidal and obviously quite asymmetric, so this is going to be a polar molecule. And then the last one is xenon tetrafluoride with 4 bonding domains, 2 non-bonding domains, and we get square planar. And because it's a square planar, xenon in the middle, fluorine in 4 different corners, these dipoles are all quite symmetric and they cancel each other out, and this is a nonpolar molecule. All right, now let's take a look at a couple of more questions about covalent bonding and orbital overlap. So the overlap of orbitals allows 2 electrons of opposite spin to share the space between the nuclei, and this is what forms the covalent bond. So in the hydrogen molecule, the orbitals that overlap to form the bond are the 1s orbitals. We can easily get this by looking at the periodic table. And in the chlorine molecule, the orbitals that overlap to form this bond are going to be 3p. And we can take a look at this and see that the 3p orbitals overlap. It gives us our bond. And in HCl, what type of orbitals overlap? Here I've got both 1s and 3p, and that seems obvious because we have combined the hydrogen and the chlorine, and so that's what we've got left there. All right, now I'm looking at this diagram to the right. This is showing the internuclear distance between hydrogens versus the energy. So when the 2 hydrogen atoms are very far apart, the potential energy approaches 0. This is way out on the far right-hand side of this graph. All right, as the 2 hydrogen atoms move closer together, the potential energy goes down. We can just see that right off the graph, and the strength of the bond increases. Okay? When the distance between the 2 hydrogen atoms becomes less than about 0.74 angstroms, and that's going to be the bottom of that energy well there, you see in the diagram, the potential energy suddenly increases sharply. And the reason that it increases sharply is because the 2 nuclei are so close together, and they're both positive, they just repel each other. So the observed bond length is the distance at which the attractive forces between the unlike charges are balanced by the repulsive forces between the like charges. And when those 2 things reach a equilibrium condition, that's our bond length. And in hydrogen, that happens to be 0.74 angstroms. All right, we'll take a look at hybrid orbitals. We'll probably just go through this one more slide before we have to stop. To explain molecular geometries, we can assume that the atomic orbitals on an atom, which is the central atom, they mix and they form new orbitals called hybrids. The process of mixing atomic orbitals is a mathematical operation called hybridization. And we fill in now the arrows in the orbital diagram for beryllium, and we see that we've got 1s2, 2s2, and then we look at part D. The beryllium atom in its ground state cannot bond with the fluorine atoms because it doesn't have any unpaired electrons. All right, we'll stop here and we'll go on to the next video.